So this circuit is called this type of circuit structure is called gain boosting, where you take a common gate and apply negative feedback around it. Okay. What is the value of input impedance? Okay. A plus 1. Okay. This is fine, everybody? Okay. So if you have a gain A, in our case, we want to build an LNA. We want $50 ohms, right? So if you want 50 ohms, in the original common gate structure, we chose for regular we specifically designed the GM such that it is 20 millisiemens, which is 1 over 50 ohms. In this case, you would have to choose, because the conductance is increasing by a certain factor, the actual value of GM that you choose would be smaller in this case by a factor 1 plus A. Okay. So basically you choose GM equals 20 millisiemens over 1 plus A. Okay. So that part is good. So now what about the noise figure? So now the Zn, choosing Zn to be 50 ohms is clear. Next part is the noise figure. Please calculate the noise figure of this circuit. Assume that A is noiseless. Okay. So you have 3 sources of noise. Find out the noise figure of this circuit. So far, okay. What happens to noise of M1? Huh? Half of it will flow through, because half of it will flow through RS, the other half will flow back through the transistor. Okay, so IN M1 by 2 the whole square. Okay, because at this point, half of it can flow back through the circuit, half of it can flow through RS. So KT gamma GM. All of these are okay? Three expressions. The output noise has three components, one from RD, one from RS, one from M1. We assume it's noiseless. Okay, so noise from RS, okay, this current has two paths to split, one back through RS itself, the other path going into the circuit. Half the current will flow through the circuit and out into the short circuit. Okay, so this will of course be correlated noise, so you have to work with amplitudes. So it will be IN RS by 2 the whole squared. Okay, so it's KT by RS. Of course, RD, all of the noise will flow through the short circuit. We are assuming that the transistor has very high output impedance, so all of RD will find its way to the output. So that is this portion. The third portion, the transistor portion, clearly at the input node, it can split between RS and the input of the circuit. Half the current will flow through the input of the circuit and into the short circuit. Okay? Because if I set GM equals 20 millisiemens by 1 plus A, what is Rin for this circuit? Rin is 1 over GM into 1 plus A, which is 50 ohms. Oops. It's 50 ohms. Okay? So as I said before, you choose a smaller GM so that your input impedance is still 50 ohms. You can, the first thing to do in an LNA is to match the input to 50 ohms. Otherwise, there's no use finding noise figure. Noise figure is always with respect to some source impedance. Okay? Okay. So what is the overall noise figure? So it is 1 plus 4 kT GD. Well, we'll just keep it as 4 kT by RD, I guess. We've always done that. Plus 1 plus, so gamma GMRS plus 4RS by RD. Okay. What was the noise figure of the original common gate? Go back to your notes and check. One plus gamma plus 4RS by RD. Okay. So now you see that the noise has come down by a factor, noise from the transistor has come down by a factor GMRS, right? Has changed by a factor GMRS. What is GM times RS? If I were to write this in a different way, oops, I'm running out of space. I'll just write it on the next. This is what you chose. So GMRS 1 by 1 plus A. Okay, it's a very small number. So what this shows is that noise figure of the gain boosted common gate is basically 1 plus, I'll write it in this form, 1 plus A plus, okay. So now as you can see, remember in the original common gate LNA, it was gamma that was causing the problem of low noise figure, or of high noise figure, right? So now it's clear that if you were able to apply feedback, okay, in this fashion, negative feedback, of course, you can improve the noise figure of the common gate structure. Okay, so this circuit is quite popular. It's about 20 years old. Okay, it is called the gain boosted common gate LNA. Just one catch, obvious catch. What is that? We assume that A is noiseless. Okay, you can never get a noiseless amplifier. Okay, so unfortunately, A adds noise. And if you try to build a low noise A, right, then what will happen is that couple of things. First of all, you have assumed that A has infinite input impedance. It will most probably have a capacitive input impedance, right? That will shift the input impedance. Okay. If you try to choose, let us say, a low noise amplifier, okay, so what kind of choices would you make for A? A common source amplifier. Okay, since you wanted it to be a low noise circuit, natural choice, it's only a common source amplifier, it is not an LNA. Okay, remember the common gate LNA produces 50 ohm input impedance without any inductors. It's a broadband circuit. You do not want to mess that up, okay, by having a real input part from the common source from A. Okay, so you can choose it to be a common source amplifier. C in of A causes mismatch because of the capacitive input impedance. Okay. So it affects high frequency S11, the input reflection coefficient of the LNA. So if you want a very low noise, what choice would you make? So the GM of the common source amplifier should be very large so that its input referred noise is very low, right? Okay, now you can see very easily how you can get into trouble, because now you need to choose a very large current, very small transistor to make sure input matching is not disturbed and you have low noise. Okay, so small transistor, small device, large current. The minute you do this, you will now have to start worrying about swing limits, etc. Okay, now normally in an LNA, this will not be a problem. Gain boosting, if you try to do this, normally it will cause swing limit problems. In an LNA, the signals are so small that the swing limit should not be a big issue. But it will, of course, affect IIP3. Okay, the swing limit itself should not be a big issue. Okay. Having said that, it turns out that you can kind of, okay, so if you have very large gain, you can see that the noise figure of this can get smaller and smaller. Okay, but the amplifier A will start adding noise. Now it turns out that there is a happy intermediate point which can be done very simply. Okay, so how do you add a gain A without any noise? transformer. Here you only need voltage gain. You do not need power gain. Okay, so the easiest thing to do is to use the transformer to apply that gain A. The only difference, yeah, you can get a 1:n, okay, but unfortunately n is limited. Okay, it's very hard to get 1 is to larger than 1 is to 2.53 on an integrated circuit. Okay, so large turns ratios are very difficult. Typically even 1:1. What happens if you do a 1:1 transformer here? You'll get a factor of half for gamma. Okay, so if you were to do this, so use a transformer, okay, so 1:1 transformer has A equals 1, which is very easy to build. A 1:1 transformer is the most straightforward thing to build. You can make it very symmetric. Okay, noise figure will basically become 1 plus gamma by 2 plus 4 RS by RD. This itself is a big deal. Okay, remember, suppose you ignore that 4 RS by RD term, right? Let's assume that that's very gain of the circuit is large enough such that that's not an issue. Okay, RD is much bigger than RS. Let's just look at the first two. We said that just the common gate LNA had a noise figure of what? 1 plus gamma. And if gamma was, I think we assumed the value of 2, worst case number of 2, right? So basically you will get noise factor of 3 and a noise figure of what? Pull out your calculators. 10 log 3. 2.2 or so, right? How much is it? 10 log 3? No, it's more, much more. 4.5, right? It's 4.5. How much is it if you have a transformer, 1:1 transformer? Huh? 1 plus 1, it will be 2, which will be 3 dB. How much will it be if you have a 1:2 transformer? It will be 1 plus 0.5. Now you can see that as you keep getting larger A, you will get lower and lower noise figures naturally. What will happen if you have a long channel MOSFET with gamma equals 0.67? The original common gate LNA would have had a noise figure of noise factor of 1.67. I think that is some 2.2 dB. That's what we calculated. Now this one will have 1.33. Calculate 10 log 1.33. 1.2 dB. Now you can see this is extremely competitive noise figures. Okay. In the case of a common source amplifier, you will get numbers like 1.2, 1.5, and so on. 1, numbers like this very easily because the FT of the device is so large nowadays. Okay. So you can see that the common gate structure can also give you very competitive noise figures. Okay. But by adding a transformer, what you have done is you have now made the circuit relatively narrow band because transformers are not wideband in general. Okay, transformers in general will operate over a specific band of frequencies. Okay, so let me just show that circuit here. How do you place the dot points? You want a negative A, right? Remember, you want negative feedback. So the dot points have to be on opposite sides in this case. Okay? Okay. Any questions? Okay. Suppose I want to maintain the broadband nature of the circuit, or at least relatively broadband nature. Okay. It is the transformer that is causing the problem. Okay. I want to figure out a passive way of doing this without the transformer. Okay. Now it turns out that if you have a differential LNA, okay, which is quite popular anyways, if you have a fully differential LNA, so now let me, oh, by the way, of course, if you are building an LNA, you would resonate the output. I have not shown that explicitly. Okay, I have not shown that explicitly. In most cases, you might be resonating the LNA if you want narrowband high gain. Okay, if you want a broadband common gate, you might do just an RD, in which case you'll be limited by RC bandwidth. I'm just pointing that out. Okay, it's possible for you to have this kind of resonance, but I will avoid showing that. Okay, now assume that you have a differential common gate LNA. I will conceptually just draw a box with a balun. Okay, but I think all of you now understand what a balun is. And I'm not showing a lot of the biasing details. I'm hoping that you folks will be able to fill in the biasing details. Okay, now let us say I have a differential common gate LNA. Okay, for this circuit, I want to do gain boosting, right? I can have a differential amplifier taking the signals from the two sources, amplifying it, giving it to the gates. I could do that. The differential amplifier would add noise, its input capacitance would cause, shifting and so on. Can you use a transformer here? Of course you can. You can use a transformer. Okay, so you can put in a transformer, primary connected at these points, secondary is connected at these points with the appropriate polarities. Oops. Okay. Now, we want to avoid the transformer because large area, etc. It turns out that, oops. You can also do capacitive coupling. Because I have a fully differential circuit. Because I have, let us say, plus V in, minus V in. What I wanted was negative feedback, such that I got some minus A times V in here. In this case, I'm just giving A equals 1, so I'm giving minus V in from the negative side of the circuit. Okay? What will happen? Each side's noise figure will go down by a factor of half. Okay, so the voltage at this node is minus V in plus V in. Okay, so the overall noise figure of each side will go down by a factor of, that gamma will become gamma by 2, right? The noise from transistors M1 and M2 will go down by half. Okay. Now the problem with capacitive coupling is that you cannot get gain more than 1. With a transformer, you could have got a turns ratio. In the case of a capacitor, the maximum gain you can get is 1. This already assumes that I have relatively large capacitors. I am showing this as infinity, but they are expected to be much larger than the CG, the input capacitance of the transistors. That's number 1. Okay. This circuit, however, is relatively broadband. You are limited by gain A, but this is broadband. I'll put it within quotes because unfortunately the balun will now limit the bandwidth of performance. Okay, remember that the antenna is still single-ended. Okay. So Vs and Rs represents the antenna receive signal and the antenna impedance. So the balun, if you can build a relatively wideband balun, then you have a truly broadband circuit. Okay, but the good thing is you can use the same LNA. The core of the LNA itself is very broadband. So what you can do if you have multiple bands of operation, let's say you have a 900 megahertz band, a 2 gigahertz band, a 700 megahertz band, etc., and you want 3 different LNAs. The LNA can be the same. You just keep changing the balun. That part is relatively easy to do. Okay. Okay. Any questions about this gain boosted common gate LNA? Okay, very good. Quick question before we move ahead. I have a single-ended LNA and I just build a pseudo differential LNA from that. All of you understand what that means, right? I have a single-ended LNA. I'm going to make a copy of that, put a balun up front, put an ideal balun up front. Okay. I'm going to find out the noise figure of the two circuits. Is it the same? Is it different? Is one better than the other? What do you think? Huh? Same. Why? Which numerator and denominator? Really? Why is that? It's not, it won't be so simple, I think. Okay, please try it out, right? Assume that you have an LNA with a noise figure, some F, noise factor F. Okay, you're going to build a pseudo differential version of that. Okay, with an ideal balun up front, ideal lossless balun. Please figure out whether the noise figure is same, different, okay, in the two cases. You will need this because your LNA project does have an ideal balun, right? So yeah, you will need to do this. Okay. In case, please try it out. In case there's any trouble, just we'll try to do it in the next class. Yes. So now you're talking about the project. Okay. Okay. Yes. Yes. Or what? Or ground them. Either one is fine. Why would it matter? Actually, it won't matter. Okay. You're only trying to make output resonance, right? It won't matter. You're not applying any common mode signal, right? So it won't matter at all. For the differential circuit, it will be exactly the same. Whether you connect the two of them together and connect them to ground, okay, or just use one single capacitor of half the value. As far as your differential input is concerned, it will be exactly the same. Yeah, correct. But I have not asked you to do anything for the common mode. So yeah. Okay. I have one LNA. Gain G, noise factor, noise figure NF. Okay. Okay. Maybe you can even assume that the output is driving 50 ohms. Doesn't matter. Okay. Now what I'm going to do, I get two outputs. Okay. What does a balun do? A balun is a 3-port network. At each port you have 50 ohms. What I can do, I take the same LNA. Okay. I want to find out the noise factor of this circuit. Okay, NF prime. That's what I want you folks to do. Understood? Okay. If you short circuit the two outputs and then find out the short circuit current, is that what you're going to do? Okay. Okay. Yeah, just confirm, do the analysis and confirm that it is the same. Okay. Okay. Also, I think there was one more question about the project somebody asked. So remember, if you are using an ideal transformer as a balun, okay, you will need a 1:√2 turns ratio. Just remember that. That's why I specifically told you folks to use just the balun itself from the AHDL lib. I hope all of you are using that. Huh? In Eldo, there's no balun. In which, how do you know there's no balun? Are you sure? The manual does not have an ideal balun. Okay. Can you put in an N port network as a sub-circuit? Of course, I'm sure you can in Eldo. What are the S parameters of an ideal balun? I have a 3-port network. There are many different ways to create an ideal balun. If you don't want to use any of the ones, you create an N port. In our case, it's a 3-port. So connect the reference to ground, port 1, port 2, port 3. Okay. By definition, for an ideal balun, ports 1, 2, and 3 are matched 250 ohms. So if you were to build the ideal 3-port S parameters, right? S11 should be 0, S22 should be 0, S33 should be 0. Agreed? In linear terms. Okay. What else? What about the other parameters? Remember, an ideal balun is purely passive and reciprocal. So S12 should be S21, S13 should be S31. Agreed? Okay. So what should the value of S13 and S21 and S31 be? If you're putting in a power P, P by 2, P by 2. Right? You expect something like this. So you put in a power P, half of it goes one side, half of it goes the other side. Make sense? Now, just confirm for yourself that the simulator is splitting power and not voltage. Okay? If it is splitting, normally that's the way it should be set up. It should be splitting power as parameters in terms of power. So these should be the ideal ones. But it's very easy to confirm that this is true. Take an N port, given some power P. You know, through the port you can give a power P. Make sure you're getting, when exactly matched, you're getting half the power. Okay? Is the ratio of? You can also define it as the ratio of powers. Okay? If you give it in terms of dB, they'll turn out to be exactly the same. Okay? The way we have defined it in class is in terms of voltage. Some microwave people do define it in terms of power. Absolutely. You given a power P. How much of the power is reflected back? Huh? Nothing. So 0. That is S11. If it's an ideal balun, how much of the power goes out here? P by 2, P by 2. Okay? So S21, S31 is half. Yes? If it is voltage, what will happen? Huh? It will be 1 everywhere. No, it won't. If the power is half, what should the voltage be? 1 by root 2. Okay, if the power is half, the voltage, if you're having voltage S parameters, it will be 0, 1 over root 2, 1 over root 2. Okay, normally the simulators deal with power, not with voltage, because everything is matched. Okay, now the last two parameters, what will they be? It should ideally be 0. You want ports 2 and 3 to be isolated from each other. Okay, so these are the ideal S parameters that you want. Okay, if you do not have an ideal balun, you can use an N port sub-circuit to split the power, or you can use a transformer with a turns ratio 1:√2. Okay, there are various ways of doing this. Okay, all I am telling you, I suggested AHDL lib because that works very well. It is just a balun. You have to define the loss, input impedance, output balanced impedance. That's all, nothing else. All of you know about Verilog? How many of you do not know the word Verilog? I hope all of you do. It's a behavioral description language, functional description language used in digital circuits. You have a similar behavioral description for analog circuits that is called Verilog A. Okay, so this description is written in Verilog A in the AHDL lib. It's a behavioral balun. It works with all your with your cadence simulator in cadence. If you are using Eldo, there must be a similar kind of balun. If not, just build your own balun or use a transformer. Okay, no problem. Okay, any other questions about the project, LNA project? How many of you have not started the project? Okay, how many of you are done with the project? Huh? Okay, what about IIP3? Okay, so just remember, you are not sure whether your results are correct or not. What does that mean?
First I plotted first order and third order, and they are linear with minus 46 dB. Then I plotted IIP values for minus 46, minus 53, and all of them should give the same value.
Are you doing a 2-point simulation? You are saying minus 46 and minus 56.
No, I did it for minus 46, then again I did for minus.
Why don't you just run a sweep? I don't understand this.
No, I didn't run the sweep. First I did the sweep to find the minus 46, like this linear is minus 46.
Okay.
Then cross check whether I'm getting IIP correct.
So what you're telling me is you did 2 points. You got some IIP3, you're taking a third point, you're not getting the same IIP3. Is that what you're saying? Okay. So first of all, for IIP3, you need to run a fairly more number of points. Okay. So first, let us quickly, if I were to plot P out versus P in, typically for the fundamental, you won't see a problem. Okay. If I look at of course, the fundamental should have a slope of 1. Okay. Actually, if you go to lower and lower powers, I know you're talking about minus 50 dBm. You should not see this at this power. But if you go to lower and lower powers, just remember that there are parasitic capacitive paths through CGD, for example, right? That may cause deviation at extremely low powers. Okay, just remember that.
There was some slight deviation above minus.
It is possible. Okay. The second thing is if you go to below minus 100, just the accuracy settings of your simulator could cause your value to be in error. Okay. So just remember these two things. Now you might see something like this, by the way. I'll show it in something like this. Maybe I don't know if you folks are seeing this. Some of you may be seeing curves like this. You may not be seeing, so this is, let us say 3 by 3, slope of 3. Maybe some of you are seeing a lesser slope. Maybe some of you are seeing a higher slope than 3 by 3, right? All of those are possible. Most probably what that means is your amplifier is more nonlinear than what you expect. That's what I suspect. Because when your third order is dominant, you should see a good 3 by 3. In this case, you don't need to extrapolate. Most probably you will find that it is going through some parasitic capacitive path. I wouldn't worry about that. Of course, here you should not be extrapolating. The whole point of IIP3 is to extrapolate at the right point where the slope is 3 over 3. Okay. It is also possible that your circuit is doing something weird. Maybe something like this also. If it is, you need to figure out why it is doing it. All these curves are unnatural. Okay. You need to figure out why it is doing it. Okay. Number two, you might be able to see gain expansion in both the fundamental curve as well as the third order curve. You will especially see this if you are operating at, you remember we discussed, right? There is a certain range of VGS minus VT over which you can see gain expansion when the sign changes. Okay. At lower VGS minus VT, remember alpha 3 becomes positive, which is when you have gain expansion, right? So if you choose very low VGS minus VT, you might see gain expansion, and that's fine as long as it's not too large. Okay, make sure it is not, a few dB is okay, 2-3 dBs of gain expansion is okay. Okay, and obviously there it is not 1 by 1 or 3 by 3. Extrapolate from the region where it is 3 by 3. That's what I want. Okay, how many of you are using cadence? A good number. Okay, about like about 1/3 of the students. Cadence you can directly plot IIP3. You do the sweep and plot IIP3 directly. In ELDO, I assume there is also a direct way to plot IIP3. How long does your IIP3 simulation take? 1 or 2 minutes? Maybe lesser, right? For your circuit, hopefully lesser. Then why only run for 2 points, right? Maybe every 5 dB, first do a course simulation from maybe, minus 90 to 0 or minus 90 to minus 10, something like that. Run the sweep. Understand the curves. Then you can use a subset where it is linear. I don't want to see minus 90 to 0 dBm, okay, for your curves. But what I want to see over a decent range where the LNA is expected to be used. Where is the LNA expected to be used? The typical dynamic range for a system would be maybe from sensitivity, which may be like, minus 100, minus 90 to about maybe like minus 40, minus 30. That will be the input power that you would expect the LNA to be able to handle. What IIP3 spec have I given? Minus 10? Yeah. So obviously you cannot sweep all the way to minus 10. If your LNA has an IIP3 of minus 10, at minus 10 your compression point is minus 20. Remember there is a 10 dB difference between 1 dB compression point and IIP3. There is no use sweeping the LNA beyond the 1 dB compression point by a large amount. You can sweep it a little bit. After that, it will become so nonlinear that your simulator will start struggling to converge. There is no use. I also don't want to see your curves. Okay. I want to concentrate on the point from 1 dB compression point down all the way till sensitivity. You understand? That's what I want to see. Okay. Okay. Sounds good. And if there are any questions, please post it on the discussion forum. Right. Hopefully we'll be able to see it and answer.